See, question number 1. From the following pairs of ions, which one is not an isoelectronic pair? Okay, so question number 1. Here what they are asking, which one is not an isoelectronic pair? So first of all, what is meant by isoelectronic? What is meant by isoelectronic species? Okay, isoelectronic species means, listen, iso means generally same. Isoelectronic means species having same number of electrons. Okay, species having isoelectronic species means species having same number of electrons. That's all, very simple. Species having same number of electrons is what we call as isoelectronic species. Okay, now same number of electrons. Right now, so in the given question, see option A. In option A, two species are given, Fe2 plus and Mn2 plus. Okay, two ions are given, Mn2 plus one species, the other one is Fe2 plus in option A. Okay, manganese atomic number is 25, right? Observe carefully. Atomic number and all you should remember, at least for the first transition series in D block. Okay, manganese and iron both belong to D block elements. For manganese the atomic number is 25 and for iron the atomic number is 26. Okay, that means neutral manganese has 25 electron, but here manganese given is having 2 plus charge. Okay, if you remove 2 electron from manganese, you will get 2 plus. So neutral manganese has 25 electron, but now manganese is given in plus 2 charge. That means 2 electron is removed from manganese. So if you remove 2 electron, then number of electron become 23. So manganese 2 plus has 23 electrons. Okay. Similarly, iron, see iron atom, neutral iron atom atomic number is 26. That means neutral iron has 26 electrons. But now iron is given in 2 plus state. That means he should remove 2 electron from this. So if I remove 2 electron, we will get only 24 electrons. Now see the two species. Are the number of electrons equal? Are the number of electrons equal? No.
No, sir.
Right. Therefore Mn2 plus and iron2 plus are not isoelectronic. They are not isoelectronic species. Okay. So for the question number 1, the correct option is itself A. The correct option is A. Anyway, we'll check option B, C, D also. See option B. In option B, 2 ions are given, O2 minus oxide ion and F minus called fluoride ion. Okay, minus charge is given. That means electron is added in the neutral atom. That keep that in mind. Oxygen atomic number 8, fluorine atomic number 9. Okay, that means neutral oxygen atom has 8 electron. But now extra 2 minus charge is there. That means 2 more electron is added. So already 8 plus 2 you will get 10 electrons. Okay. Fluorine, neutral fluorine atomic number 9. That means neutral fluorine atom has 9 electron. But here it is given fluoride F minus. That means extra 1 electron is added. Okay. So 9 plus 1, 10 electrons. Now see, oxide and fluoride, they have same number of electrons. Okay, they are isoelectronic. Option B is isoelectronic. What about option C? In option C, we have sodium plus and magnesium 2 plus, Na plus and Mg2 plus. Sodium atomic number 11, magnesium atomic number 12. Okay, now sodium, neutral sodium has 11 electron, but now sodium is given as +1. That means one electron is removed from sodium atom. So sodium ion has only 10 electrons. Similarly, magnesium 2 plus, neutral magnesium atomic number is 12. Okay, it has 12 electron, but now magnesium is given in 2 plus state. 2 plus means 2 electron is removed from magnesium atom. That's the meaning. Okay, so if I remove 2 electron from 12, I'll get 10 electrons. That means Na plus and magnesium 2 plus, they are also isoelectronic. Okay, then what about option D? In option D, two species are given, Mn2 plus and Fe3 plus. Just note the charge carefully. Okay, very important. Manganese atomic number 25 I have told you already, right? 25. Okay, so manganese atomic number, neutral manganese has 25 electron, neutral, but now it has 2 plus charge. That means we should remove 2 electron. So 25 minus 2, you will get 23 electrons. Okay, iron atomic number 26, that is neutral iron atom has 26 electrons, but now it carries 3 plus charge. That means you should remove 3 electrons. So 26 minus 3, you will get 23 electrons. So see here, these two are isoelectronic, these two are isoelectronic, these two are isoelectronic. So these options B, C, D have isoelectronic pairs, whereas option A, in which number of electrons are not equal, so this is not an isoelectronic pair. Okay, take down. So for question number 1, the correct option is A. Isoelectronic species means species having same number of electrons. Is this clear? Right. Now
Yes,
let me
sir,
go
sir.
to the next question. Yes.
1 minute, sir.
Yeah.
Yes, sir.
Yeah. Now let me go through question number 2. See question number 2. In question number 2, they are asking the number of protons. Okay, the number of protons, neutrons and electrons in lutetium respectively are. So the given species, question number 2, the given species is lutetium. Okay, lutetium, for lutetium atomic number and mass number are given. Atomic number is 71 and mass number is 175, mass number. Okay, students, observe carefully. Atomic number, since it is the neutral atom, okay, lutetium is now there is no plus charge or minus charge given here, so it is a neutral atom. Therefore number of electrons, okay, is equal to number of protons. In the case of neutral atom, number of electrons and number of protons are equal. That is equal to atomic number Z. Okay, in the case of neutral atom, number of electrons is equal to number of protons, which is equal to the atomic number of that atom. So for this atom, atomic number is 71. Therefore number of electron is 71, number of protons also 71. Okay, so number of electrons equal to 71. This is atomic number Z and this is mass number A. Okay, we represent atomic number by the symbol Z and mass number by the symbol A. So number of electron is 71 because atomic number is 71. Number of protons also equal to 71 because it's a neutral atom. What about number of neutrons? Number of neutrons. Number of neutrons is the difference between the mass number and the atomic number. Okay, mass number given is 175, atomic number given is 71. So if I subtract, I'll get 4, 5 minus 1, 4, 17 minus 7, 10. So we'll get 104. This is the number of neutrons present in the atom.
Option A, sir.
They are asking number of proton, yes, 71, 104, 71, option A. Yes, you are right. That's all good. So the correct option for this question is A. Now just go through question number 3. Question number 3, beryllium 2 plus is isoelectronic with which of the following ions they are asking. So what you have to do, first you take beryllium 2 plus. See, let me write here, question number 3. In the case of beryllium 2 plus, okay, in the case of beryllium 2 plus, beryllium atomic number is 4. Remember that. Beryllium atomic number is 4. That means neutral beryllium has 4 electrons. But now beryllium is given a charge 2 plus. Okay, positive charge means you should remove electron. So 2 positive charge, 2 plus is given, therefore we should remove 2 electron. Therefore beryllium 2 plus contain only 2 electrons. Atomic number is 4. 4 minus 2, 2. Now what we have to do, among the given species A, B, C, D, you need to identify which one has 2 electrons. So among the given options, in option A, H plus is given. H plus atomic number is 1. Therefore number of electrons is 0 because atomic number 1, charge is plus 1. So 1 minus 1, 0. In option B, lithium plus is given. Lithium atomic number 3, positive charge, 1 plus charge is there. So 3 minus 1 is 2 electrons. 2 electrons. For Na plus, sodium atomic number is 11. 11 and 1 plus charge is there. So 11 minus 1 is 10 electrons. Okay. And for magnesium atomic number is 12. So 12 minus 2, 10 electrons. Now, okay, beryllium 2 plus is 2 electrons. So which species among the 4, which species has 2 electron? It is the lithium ion. Therefore lithium ion is isoelectronic. Lithium plus is isoelectronic with the beryllium. So the correct option for this question is option B. Okay, take down. So see question number 4. In question number 4, they are asking isoelectronic species. Okay, in option A, 4 species are given: carbon monoxide, cyanide ion Cn minus, NO plus ion, and C2 2 minus ion. Okay, 4 species are given in option A. Listen, carbon atomic number 6, oxygen atomic number 8. So 8 plus 6, 14. So carbon monoxide has 14 electrons. Okay. Cyanide, carbon atomic number is 6. Observe carefully. Carbon atomic number is 6. Nitrogen atomic number is 7. 7 plus 6, 13. 13, and here one minus charge, extra minus charge is there. That means you should add 1 electron. So 13 plus 1, 14. Okay. NO plus, nitrogen atomic number 7. Oxygen atomic number 8. 8 plus 7, 15. 8 plus 7, 15, and 1 positive charge is there. Positive means you should subtract. So 15 minus 1, 14 electrons. Okay. Then carbon, here 2 carbon atoms are there. C2 means 2 carbon atom. Each carbon has atomic number 6. 2 carbon, therefore there are 12 electrons. Okay, and you have 2 minus charge also. So extra 2 electron we should add. So 12 plus 2, 14 electrons. Okay, see, in this option, option A, all the 4 species have same number of electrons. That means, okay, these species are isoelectronic. They are isoelectronic species. They are isoelectronic species. Take down. Take down. In a similar manner, you try to identify is there any other option, okay, having same number of electrons. For Question number 4, the correct option is A. Okay, you just check it out whether what about other options. Okay, do they have same isoelectronic species or not, right? Then question number 5 and 6, they are also comes under isoelectronic basis questions, so you try to do it. Okay. Question number 7, a particular station of All India Radio, New Delhi, broadcasts on a frequency of 1368 kilohertz. Frequency is given. Question number 7. Frequency new is given, which is 1368 kilohertz. Okay, and what they are asking, the wavelength of the electromagnetic radiation emitted by the transmitter is. Okay, they are asking the corresponding wavelength. Frequency is given, they are asking wavelength. You know very well, frequency nu is equal to C by lambda. Nu is equal to C by lambda. Okay, it's a very simple relation. So if you want wavelength lambda, then lambda is equal to C by nu. This is the formula. Okay, and you know the value of velocity of light in SI unit is 3 into 10 to the power 8 meter per second. Okay, and what about the frequency? Frequency is given in kilohertz. So kilo means 1000. Okay, to convert kilohertz into hertz, you have to multiply by 1000. So 1368 into 10 power 3 hertz. Okay, hertz is nothing but per second. Okay, 1368 into 10 power 3 per second. Right, so I'll substitute this value here. So 1368 into 10 to the power 3 second inverse. Okay, so if I divide these two, second inverse cancel. Okay, so 3 by 1368, or you can also write this as roughly 3000. I can write numerator as 3000 into 10 to the power 5 divided by 1368 into 10 to the power 3. Okay, so 3000 divided by 1368, it will come roughly 2000 or 200 and something. Okay, 200 something. So you just work out carefully and try to identify the answer. Let me give the answer directly. So the answer comes out as 2.1929. Okay, 2.1929 into 10 to the power, here we have 5 in the numerator, here we have 10 power 3. If 10 power 3 goes to the numerator, it will become 10 power minus 3.
Minus.
You'll get 10 power 2, right? 10 power 2. So if you multiply by 100, you will get 219.2929 meters. You will get the answer in meters. Okay, so which option matches exactly with this? See, 219.29 is there. So if you round off this, I can write it as 219.3 meters. If you round off, you will get 219.3 meters. So the correct option for this question is option B. Option B. Okay, option B and option C are very close. Just see that carefully. Option B and option C are very close, but since it comes out as 219.29. Okay, if you round off, you will get the answer as 3. So the correct option for this question is option B. Right, take note. Question number 8. Which of the following series of transitions in the spectrum of hydrogen atom falls in the visible region? You know very well, in the hydrogen spectrum, I have told you that in hydrogen spectrum we have different series of lines. In the hydrogen spectrum, we have different series of lines. What are they? Lyman series, Balmer series, Lyman Balmer bracket Passion series bracket series, Fund series, PFUND Fund series, then Humphrey series. Okay, so in hydrogen spectrum, right, we have these series of lines: Lyman series, Balmer, Passion, bracket, and I have told you Lyman series appear in ultraviolet region of the spectrum. Okay, these lines appear in the lower wavelength. Ultraviolet means lower wavelength region. Balmer series, Balmer series lines appears in the visible region of the spectrum. Okay, all other lines appear in IR. Passion, bracket, Fund, okay, all other lines appear in the IR region of the spectrum. Okay, and you know very well, in Lyman series, lower level should be 1, higher level can be anything. For Balmer series, lower level should be 2, higher level can be 3, 4, 5, etc. Okay, likewise for Passion, bracket, Fund series, you know what is the lower level and what are the possible higher levels. Okay, so remember this is very important. So for this question number 8, which of the following series of transitions in the spectrum of hydrogen atom falls in visible region? Yes. Balmer. Okay, so the correct option for this question is option C, right? Take down option C. Question number 9, calculate energy in joule corresponding to light of wavelength 45 nanometers. Wavelength is given, they are asking energy. Okay, so what are the possible options? Okay, first I'll work out this. I'll give you the formula. Calculate question number 9. Let me do it in the next page. Yes, question number 9. Calculate the energy in joule corresponding to the wavelength of 45 nanometer. See here, I like to give two formulas. You just remember this. If you want energy, okay, if wavelength is given, then you can use this formula: E is equal to hc by lambda. E is equal to hc by lambda will give you the relation between energy and wavelength. Okay, suppose if wavelength is given in nanometers, students observe carefully. If wavelength is given in nanometer, and if you want energy in electron volt, see, energy in electron volt, observe carefully. What you have to do, you must put hc value in electron volt nanometer, and the value is 1240. Observe carefully, student. This is a very useful relation. Try to remember this. If wavelength is given in nanometer, if you want energy in electron volt, then use this formula: 1240 by lambda. Okay, 1240, right, is nothing but the value of hc. The value of hc is 1240, okay, electron volt nanometer. So denominator also nanometer cancel. Okay, remember this is a shortcut formula. Similarly, if you want energy in joule, okay, it's very simple. 2 into 10 power minus 16. Students observe carefully. 2 into 10 power minus 16 divided by lambda in nanometer. Simple. Very simple relation. 2 into 10 power minus 16, okay, divided by wavelength in nanometer. You will get the answer in joule directly. So remember both these formulas. Both are very important formulas. Okay, very useful for calculating energy. If wavelength is given in nanometer, you can calculate energy in electron volt. If wavelength is given in nanometer, you can calculate energy in joules directly. Now see, in this problem, calculate energy in joule corresponding to the light of wavelength 45 nanometer. Okay, So wavelength is given 45 nanometer. They are asking energy in joule. So if you want energy in joule, use this formula, 2 into 10 to the power minus 16 over value of lambda is given in nanometer, which is 45 nanometers. So it is simply 2 by 45, or you multiply, just make this into 200. I multiplied this by 200 and divide this by 100. Sorry, I multiplied 2 by 100 and I'm going to divide this by 100, so you'll get 10 power minus 18 by 45. Okay, just to cancel, that's all. Very simple. So you can use 5 table. 9 5s are 45. Here 4 5s are 20. 0 40. 40 by 9. 9 4s are, yeah, 9 4s are 36 minus 40. It comes out as 4.4 into 10 power minus 18 joules. Roughly it comes out as 4.4 into 10 power minus 18 joules. Take note. So what are the options given? 6.67 into 10 power 15. Can you tell me which is the correct option in this? The correct option for this question is option D, 4.4 into 10 to the power minus 18 joules. Okay, take note. Right, see question number 10. Value of Planck constant is given 6.63 10 power minus 34 joule seconds. The speed of light is 3 into 10 power 17. It is given in nanometer now, nanometer per second. Which value is closest to the wavelength in nanometer of a quantum of light with the frequency 6 into 10 power 15 second inverse? Okay, yeah. So frequency is given. See which value is closest to the wavelength in nanometer of a quantum of light with the frequency. Frequency is given. They are asking the wavelength. Okay. So this problem, similar problem we did already. Anyway, let me show you the method. So question number 10. Right. What's the question? Frequency is given now. So frequency nu is equal to, frequency is given, the value is 6 into 10 to the power 15 second inverse. This is the value of the frequency. Okay, and they are asking wavelength. You know very well, nu, they are asking wavelength. Okay, they are asking wavelength in nanometer. They are asking. Okay, so how to get the value? So you know the relation, nu is equal to c by lambda, right? Or I can write lambda is equal to c by nu, and the value of c is given in nanometer, which is 3 into 10 to the power 17 nanometer per second, and the value of frequency is given, which is 6 into 10 to the power 15 second inverse. Okay, second inverse cancel, right? So if you cancel these two, 1 3s are 3, 2 3s are 6, 1 by 2. So 1 by 2 is nothing but 0.5 into 10 power 15. If I bring it to the numerator, I will get 10 power 2. Correct? 10 power 2. If I multiply this by 100, I will get 50 nanometers. Okay, take note. So the correct option for this question is option A. See question number 11. Question number 11. Question number 11. According to law of photochemical equivalence, energy absorbed in erg per mole is given as H value is given in erg, C value is given, Avogadro number is given. See, so they are asking some relation, that's all. See, student, E is equal to Hc by lambda will give you energy of 1 photon. But here they are asking energy in for 1 mole of photon. Per mole is given, okay? Erg per mole. So they are asking energy in erg per mole they are asking. If you want energy per mole, you have to multiply by Avogadro number, that's all. So H into C into Avogadro number by wavelength. Okay, and it is given that H value is 6.62 in 10 power minus 27, C value 3 into 10 power 10, and Avogadro number 6.02 into 10 power 23. If you multiply all these three in the numerator, we get this answer, 1.196 into 10 to the power 8 by lambda. Okay, take note. So it's a very direct question. Take note. Since h value is given in erg, okay, and velocity of light c is given in centimeter per second, okay, so the numerator in this case, right, has the unit of centimeter. If you put wavelength in centimeter, then the energy will get the unit of numerator is erg per mole centimeters. This is the unit of numerator. In the denominator, if you put wavelength in centimeter, okay, you will get the energy in joules, erg per mole. Okay, take note. So for this question, the correct option is A.
Can you repeat it?
See, in question number 12, energies are given. E1 is 25 electron volt, E2 is 50 electron volt. Okay, the energies of E1 and E2 of two radiations are 25 and 50 respectively. They are asking the relation between their wavelength, right? So you know the general relation is E is equal to hc by lambda, or I can say E is inversely proportional to lambda, because h and c are constant. So if energy is 25 electron volt, so 25 is proportional to 1 by lambda 1. I'll take the wavelength as lambda 1 when energy is 25. If energy is 50, let us take the wavelength as lambda 2. So the relation is 25 proportional to 1 by lambda 1, 50 proportional to 1 by lambda 2. Now I am going to divide this by this. So here we have left hand side 50, here we have left hand side 25, so 50 by 25 equal to, here in the right hand side we have 1 by lambda 2, here in the right hand side we have 1 by lambda 1. So if I simplify this, you will get 2 by 1 here. In the numerator we have 1 by lambda 2 in the right hand side. If you bring 1 by lambda 1 to the multiplication, you get lambda 1 by 1. So 2 is equal to lambda 1 by lambda 2 we get, or lambda 1 equal to twice lambda 2. Okay, so the correct option for this question is option B. Value of Planck constant is given 6.63 10 power minus 34 joule second. The velocity of light is given. Which value is closest to the wavelength in nanometer of a quantum of light with the frequency 8 into 10 power 15 second inverse? Okay, so frequency is given and they are asking wavelength in nanometers. Okay, yeah, so very simple question. We have already did similar type of questions. Question number 13. Observe carefully. Now the frequency given is 8 into 10 to the power 15 second inverse. This is the frequency given. Okay, what we need to do? We need to calculate the corresponding wavelength in nanometer. We want wavelength in nanometers. How to get the value? Okay, you know the relation between nu and lambda. Nu is equal to c by lambda. So we are using the same formula again and again. Okay, so what is lambda from this? From this, lambda is equal to c by nu. C value is given. C value is 3 into 10 to the power 8 meter per second. Okay, and frequency value is 8 into 10 to the power 15 second inverse. Second inverse cancel. Okay, so you will get 3 by 8 into if you simplify this, and one more thing, they are asking wavelength in nanometer. Okay, but in the numerator we have meter. To convert meter into nanometer, you should multiply this by 10 power 9. Very simple. By 8 into 10 power 15. I'll keep denominator as such. Numerator I am multiplying by 10 power 9 so that you will get the wavelength in nanometers. Okay, so lambda is equal to, see here, 10 power 8, 10 power 9. So if you add, you will get, if you multiply, you will get 10 power 17. And in the denominator we have 10 power 15. If you bring it to the numerator, it will become 10 power minus 15. So 17 minus 15 become 10 power 2. 10 power 2. So I can write this as 3 into 10 power 2 by 8, or 30 into 10 by 8. Just for simplification I wrote like this. Okay, so what we get, 4 2s are 8, 15 2s are 30, 15 by 4, 3 point, okay, 33.7 something it will come, right? 3.75 into 10, or 37.5 nanometers. 37.5 nanometers roughly. Take note.
Okay, sir.
Yes, 37.5 is close to the option C, which is 4 into 10 40 nanometers. So the correct option for this question is C. Okay, take note. Then question number 14.
1 minute, sir.
Yes. Question number 14. For a given energy E is equal to, for a given energy E is equal to, energy value is given, E is equal to 3.03 into 10 to the power minus 19 joules. Energy is given. They are asking the wavelength, corresponding wavelength. And see, in all the options, A, B, C, D, wavelength is given in nanometers. So that means they are asking wavelength in nanometer. Okay. And I have given a shortcut formula for energy in joule and wavelength in nanometer. The formula is this: energy in joule is equal to 2 into 10 to the power minus 16 by wavelength in nanometer. Very simple, direct relation. Okay. Now energy is given in joule. The answer, the value given is 3.03 10 to the power minus 19. Okay. 2 into 10 to the power minus 16 by, we need to find out the wavelength in nanometers. Wavelength in nanometer. Bring lambda here and bring this quantity here. So wavelength in nanometer is equal to 2 into 10 to the power minus 16 over 3.03 into 10 power minus 19. If 10 power minus 19 goes to the numerator, it will become 10 power plus 19. 10 power 9 plus 19, 10 power minus 16, you will get 10 power 3. So 2 into 10 power 3 is 2000. 2000 by roughly 3. 3.03, you take it roughly 3. So you will get 20 by 3 is 6. Again 226, 6, 6, like that it will come. It will come roughly like this. Nanometers. Okay, take note. Okay, so 656 nanometer is close to the answer. So the correct option is D. Correct option for this question is option D. Is this clear? This relation is very important. Remember this relation. Okay, you can answer the question directly. Yeah, see the next question. See question number 15. What will be the longest wavelength line in Balmer series of spectrum? Longest wavelength line in Balmer series. A very simple question. Question number 15. Okay, they are asking longest wavelength. Okay, in Balmer series, you know very well, for Balmer series, lower level n1 should be equal to 2. Lower level should be 2. Higher level can be anything, 3, 4, 5, up, it can even be infinity. Okay, student, observe carefully. 3 to 2 transition will give longest wavelength because energy difference is low, so you will get longest wavelength. Infinity to 2 will give shortest wavelength. See, 3 to 2 transition will give longest wavelength radiation. Longest wavelength. Right? Whereas infinity to 2 transition will give shortest wavelength. Shortest wavelength. Right? Because 3 to 2 energy difference is small. Energy difference small means wavelength should be large. Okay? So longest wavelength. And in the question they are asking what will be, see question number 15, what will be the longest wavelength line in Balmer series of spectrum. So that corresponds to 3 to 2 transition. You know very well wave number formula nu bar equal to Rydberg constant for hydrogen atom into z square into 1 by n1 square minus 1 by n2 square. This is the formula. Okay. Now what I am going to do, I will keep this nu bar as such, Rydberg constant as such, and it is given hydrogen atom. What will be the longest wavelength line in a Balmer series of spectrum? So in the case of hydrogen atom, let us assume the atom is not mentioned here. So let us assume the atom is hydrogen atom. So in the case of hydrogen atom, this is 1 square is 1, and for Balmer lower level should be, this transition will give longest wavelength, so lower level is 2 here, 2 square is 4, I'm sorry, 2 square is 4 minus the higher level is 3 square is 9. Okay, so nu bar equal to RH into, if I make LCM here, I'll get 9 minus 4, that is 5 by 36. 5 by 36, and we want wavelength. You know very well, reciprocal of wave number is wavelength. Okay, so if you want wavelength, nu bar is nothing but 1 by lambda. So 1 by lambda is equal to RH into 5 by 36. So if you want wavelength, what to do? I'll write here. So wavelength, I'll write here. So lambda is equal to, okay, we should take the reciprocal, 1 by RH into reciprocal of 5 by 36 is 36 by 5. Right? Just take the reciprocal. And you know very well, 1 by RH value I have given already, which is 91.1 nanometer. 91.1 nanometer into 36 by 5. Okay, so if you simplify this, you will get the wavelength in nanometer directly. Let me give the answer. 91.1 is, we have only just divided by 5, so it is very easy. So I am not going to do that. I'll give you the answer directly, which is 91.1. Yes, it comes out as 655.92 nanometers. That's the wavelength. Okay, take down. So the answer which is close to this is 656. 656 is option B. 655.9 is close to 656. So the correct option for this question is option B. Okay, take down.